Can you hear me now?
Yes.
Yes.
Yeah, now we can hear you.
Okay. Sorry, but I have no idea what happened, to be honest with you. I don't know why. I didn't do anything to the computer. It's just now you can hear me before you couldn't. Okay, sorry about that. Okay, so let's go back. What I was saying. Okay, I was telling you that your exam, as you know, is on Friday. And I'm telling you just to start reviewing. Do not wait till Thursday at 8 o'clock to start the review. It doesn't help you. Get going. And if you have any questions, please let me know so I can help you as you are reviewing. And your quiz 3 is on Brightspace as well as the solution. Please, those who didn't do well or did any mistake, make sure you get your mistake so you won't repeat it on the exam. All right, so today I was planning to do 2 sections. I hope I can do both. They are simple in nature, so I'm not concerned about them 2 sections. The first is section 6.4, length of a curve, because they are basically formula that you have to apply. So what is a curve? A curve is nothing more than you take your pencil and you start drawing something. Okay, you draw, you get a curve. This is really what a curve. So what's the length of a curve? What do I mean by a length? You take this curve and you just basically stretch it and you measure it. That's really what the length of a curve. So if my curve happened to be a line segment, something like that, so the length of a curve is nothing more than the distance from here to here. So that's the length of a curve in a very simple scenario. So our question today is basically, if you have a line segment, it's easy to find its length. If you have something that's curving, something like that, and the question is how to find the length. So if you have a line segment, it's easy. You can use basically Pythagorean theorem. That's how you find the length. So you measure from here to here, you measure from here to here, and you basically use Pythagorean to find the length of the line segment. When things start curving, okay, there is a problem. How I'm going to measure? I'm not gonna, of course, stretch it. I have to find a way to measure this without actually stretching it. So our problem is going to be the following. That's our problem. So length of the graph of a curve, of the graph of a function. So my curve is going to be the graph of a function for x between a and b. So that's really our problem, length of the graph of a function for x between a and b. So my problem is the following. I have a function. Okay, that's the graph. That's my a, and that's my b, okay? And I need to find the length of this curve. The curve is the graph itself. So how can I do it? So this is y equal f of x, and this is something that is curving. How can I find the length of a curve? The only thing I know how to find is a line. How can I find the length of a curve? Any ideas? What shall I do with it?
Do you take like the length of multiple lines and then add them together, maybe?
I have now. How can I? Where can I come with the lines from? You're absolutely correct. What shall I do? Where can I get the lines from?
From the graph, you just draw them like it's like drawing like perpendicular to it or something like that, or like I'm not sure, to be honest.
Okay, we're gonna do it lines, absolutely lines. But how are we? Where are we gonna get our lines from? As simple as that. We're gonna take this curve and cut it into pieces. I may draw another picture. And then what I'm gonna cut? I'm I'm going to start join those points by lines. Join them. By lines. By lines. Something like that. Join them by line. And so this is the line. This is my line, my line, my line. So I'm going to do the lines in red so we know the lines. Okay. And a line, I know how to find the length of a line. So instead of finding the length of the curve, it's curving. I have a problem. So what I'm going to do is basically find the length of every one of those line segments and add the sum of those line segments. So finding something curving is difficult. So we approximate it by something which is easy to compute, which is a bunch of lines. That's really the strategy. That's how we always will be doing those problems. We have something that we don't know what to do. We break it into pieces that we know how to handle, and then we add the length of those small little pieces. Now, how are we going to do that mathematically? We're going to basically start by dividing the interval AB into pieces. So I'm going to call this X1. I'm going to call this is X2. X3, and general, I'm going to focus on one line segment. I'm going to call this Xi, and this Xi plus 1, and this is my Xn. So I'm going to divide the interval AB into pieces. So every point here, so I'm going to take this point, I'm going to call it Pi, for example. So I'm going to call this P0, I'm going to call this P1, and I'm going to call this basically my typical line, Pi, and this is Pi plus 1. Now, what are the coordinates of the point Pi? And what are the coordinates of the point Pi plus 1? And this we're going to call this point Pn. So the point Pi will be helpful coordinate xi and the value of the function at xi. Xi plus 1, sorry, this is xi plus 1, and this is xi plus 1. This point, this is xi here, so this will be xi f of xi. And now what is the strategy? The strategy is first, find the length of a typical line segment, of the line segment Pi plus 1. That's the strategy. Second, add the sum, add the length of the Pi plus 1. And then this will give a Riemann sum. That's really the strategy we're going to use. Okay, so the idea is I'm going to compute the length of this, compute the length. I'm going to add all those up. Adding them will lead me to Riemann sum, and then this will be transformed into an integral. Right? So I'm going to focus, as we always did, on a typical line segment, very one of them. And I'm going to compute the length of this line segment, and then I'm going to add up all of them. So I'm going to focus here on one line segment. So this is, let me assume, so I'm going to basically just take this piece and think about it. Okay, what's the length of Pi plus 1? So let me draw it here. So suppose this is Pi, this is Pi plus 1, and this is my curve. So I'm going to basically take this one and zoom. The idea is take this piece here and zoom it a little bit so you know exactly what I am doing. So let's assume this is my Pi, Xi f of Xi, and this is my Pi plus 1. Of Xi plus 1. Okay, and let's compute this. Okay, let me compute this. What's the length of Pi plus 1? Is equal to what? All right, I'm going to use Pythagorean. What's the length? The length is, by Pythagorean theorem, is the square root of the side from here to here plus this. That's what it is. How much do we have from here to here? And how much do we have from here to here? Anybody?
F of x I minus f of x I plus 1.
Okay, it's the difference between f of xi, so we're gonna call it delta y, absolutely, and we're gonna call it f of xi minus f of xi plus 1. Anybody agree with him? So you can call this a delta y. How much do we have from here to here?
It's just like delta x. So
That's
it's,
our famous delta
yeah.
r. It's in this problem, it's because right minus left. Xi plus 1. Okay, it's basically Pythagorean theorem. So the distance from here to here is going to be the square root of delta x square, if you want, instead of really dragging this, plus the delta y square. Okay, this is from the picture itself. All right, so I'm computing the length of every little line segment. All right, so S is equal to what? Now I'm going to manipulate tiny bit. That's the only piece of algebra I'm going to do. I'm going to factor out the delta x, because you know those Riemann sum always need this delta x. I'm going to factor out delta x squared. This would leave me 1 plus delta y. So I factor this out over the delta x, and this is squared. Okay. So finally it's going to be equal to, now the delta x squared, I can really get it out of the integral. So this piece here, we're going to get it out. So I'm going to multiply by delta x. I just want to move to the right. And I will have that. So I'm focusing on pi plus 1. Now, I'm going to take this expression by itself, and let us see what this is. So this expression is basically f of xi. Because it's square, I'm going to put f of xi plus 1 minus f of xi. In this problem, it doesn't really matter, because at the end, I'm going to square this. So even if I change the sign here, divided by xi plus 1 minus xi. And now I'm going to ask you a little bit of a question. Does this ratio remind you anything?
The derivative equation?
What?
Is the equation for derivative?
It's the equation of the derivative. Exactly. It's basically the change in y over the change in x. It's really the derivative. So this is almost equal to, this should remind you the slope of the secant line. That should remind you the slope of this line, because that's the delta y over the delta x. And we know that this is basically the derivative when delta x is very small. This is almost equal to the derivative at xi when delta x is small. Okay, so this square root, so now I go back to that. So this is almost equal to 1 plus. So the delta y over delta x, this is nothing more than what the derivative is when delta x is small. So this is 1 plus the derivative at xi square times delta x. Right? So in my little picture here, this line segment here, pi plus 1, so the length of that, so the length of this piece is the square root of 1 plus the derivative at xi times the delta x. That's the length of the little piece right there. Now, the length of the whole arc is is approximated by the sum of the length of those line segments. So now the length of the curve, is almost equal to the sum of length of the line segment. The line segment, okay, which is equal to the sum of those. This is the length of every one of them, of the square root of 1 plus f prime of xi square delta x. 1 to n. Now, of course, when delta x becomes small, we have a much better approximation. The smaller the delta x, it means the more subdivision, the better approximation we have. Because if we don't have a lot of approximation, this is not a good, this line segment doesn't approximate the curve. So if we have a lot of them, we can almost cover the curve, almost cover the curve. So the more approximation, the more subdivisions we have, means the smaller this delta x is, a better approximation we have. So the length of the curve is the sum of that, which is equal to this, which is now, that's really the Riemann integrals that we are always after. So the actual length of the curve given by the graph of f of x for x between a and b is equal to, so the length of the curve given by the graph of f of x for x between a and b is equal to the integral of the square root. So this will become a dx 1 plus the derivative. That's important. That's the derivative square integral from a to b. So length of the curve given by the graph of f for x between a and b is given by this integral. So that's really the formula that how we derive the length of the curve. So I just give it to you, it's like intriguing. Where does this derivative come from? And the derivative is really based on, what we did. It's basically, again, it's the axiom of partitioning, approximating the length by the sum of the lengths of object that we know. All right, so now we're going to do one simple example because it's really a formula. What matters here is to know how to apply it and to be able to integrate appropriately. So I'll take a problem and we proceed. Questions? So example. The only issue with those, actually, this formula is that the formula, when we use it, we end up with very hard integrals. So for that, I will only give you very simple problems concerning this section. So the question is, find the length of the graph of the function, the length of the graph of the function f of x equal to square root of x cubed from x equal to 1 to x equal to 4. So basically, we have this curve would look something like that. That's how the curve looks like. This is 1 here, and this is 4. And you want to find the length from here to here. So even the picture is not really very much needed in those problems because it's boiled down to applying the formula. So what is the length? Is the integral from 1 to 4 of the square root of 1 plus the derivative squared dx. So to find this length, we have to find the derivative first, square it, plug it in here, and then integrate. So first we find the derivative. So let us do that. What is f prime? So this is f. To find the derivative, I have basically, as I said, derivative doesn't like the square root, so I have to rewrite this as 2 times x to the power 3/2. So that's f of x. So now I need to find the derivative. What is f prime? It's 2 times 3/2 times x to the 3/2 minus 1. So that's 3x to the power 1/2. And now we plug it in. So we first find the derivative on the side, and when we plug it in. So now what is the length? Is the integral from 1 to 4 of the square root of 1 plus derivative square. It means 3 square root of x if you want. Okay. This is equal to the integral from 1 to 4 of the square root of 1 plus. Now 3 square root of x times 3 square root of x will gonna give me 9x, the whole thing dx. So we end up with this type of integral. Now we have to compute it, and very quickly, how would you compute this integral?
Wouldn't you just separate the 1 and the 9 from the equation, just getting you dx and a x?
Okay, I'm glad you said it, because we have to finalize this once and for all. Can we separate it? That's what you saw.
Oh wait, never mind. No,
Can we separate it?
I don't think so. No.
Absolutely not. I don't want to see that again. All right, crucial. Believe me, if we can do that, what the section we're gonna study after we finish this, after the exam, will not be needed. Math will be very easy, very easy. Okay, and it's simple. I mean, if you take square root of 9 plus 16, that's the square root of 25, which is a 5. This is definitely not that, which is 3 plus 4 equal to 7. Absolutely not. We cannot break the square root if you have a sum. We cannot break the square root if we have a sum. Okay? All right, so what do we do?
Substitution.
Absolutely. Substitution is the way to go. Substitution is the way to go. So we're going to set u to be 1 plus 9x. My du is 9 dx. And since I know I only have the dx, so I'm going to isolate it. 1 over 9 du equal the dx. Then I would like to change the limit at the beginning. You don't have to. If you want, you can do it, or you can stay till the end. Let's change them. When x is 1, I plug in 1 in here. I'll have 1 plus 9, which is 10. That's for the lower limit. For the upper limit, if x is 4, then my upper limit will become 1 plus 9 times 4, which will give me a 37. And then my integral will become, so the length will be equal to. Now then, since I changed my lower limit, so my 1 now is at 10, my 4 is at 37, the square root of u, the dx will become 1 over 9 du. No, because I did that, I don't have to, I forget about x, because I changed my limit. And now this is a simple integral in u, a definite integral in u. Now, as we know, the u has to become u to the power 1/2. And this would give me 1/9, 1/1/2 plus 1, u to the power 1/2 plus 1. And this is evaluated between 10 and 37. So finally, I will have 2/27, 37 to the power 3/2. Nasty number, but who cares? Minus that, okay, and of the problem. All right, so it is a simple formula to apply to find the length. The difficulty, I'm telling you that ahead of time, it generates very hard integral. That's why the problems are made up so that you guys can compute the length of the curve. Part 2 is, sorry. Any questions? Part 2 is the notion of surface area. So 6.5, as I said, the sections are really simple because they are basically two formulas. Surface area. So first, we saw the idea of an arc length. How do we measure the length of an arc? Now the surface area. First, let us remember, what does surface area mean? What does surface area mean? Surface area is nothing more than the area of the outer layer of an object. That's what the surface area is. It's the area of the outer layer of an object. So for example, if I have a simple cylinder, that's a cylinder. So if I have a cylinder, not shell anymore, just a cylinder. Okay. So what's the surface area of, so that's a cylinder, that's R, and that's the height. So what is the surface area of a cylinder? What do we mean by that? The surface area is basically the area of the outer layer. It means if you take the cylinder and you cut it, really basically physically cut it, you have a knife and you cut it, you have a scissors and you cut it, and you open it, you're gonna get a rectangle, honest to goodness rectangle. That is not a shell this time, it's just a cylinder, there is no thickness attached to it. So the surface area of the cylinder is actually the area of this rectangle. So the surface area, this becomes, so the surface area of a cylinder is nothing more than the area of the rectangle. That's really what the surface area is, which is in this case, as we said last time, if you open it, so that's the H, and this cylinder, the width from the length from here to here is nothing more than the circumference of the cylinder. So this is the 2 pi r. And this will become 2 pi RH. Okay, so that's really what the surface area is. So let me take another picture. I'm not going to really, if I take a cone, for example, I take a cone. Okay, that's a cone. And what's the surface area of a cone? So it's exactly the same thing. You take the cone and you cut it. You cut it and you open it. So cut and open. What do you think you get? Any idea?
A triangle?
Kind of a triangle. Kind of a triangle. We get something like a sector usually because there is a curve in the top. So it's not quite a triangle. We get something like that. Actually, imagine I give you a sector like this and I tell you to fold it. If you take this one and you fold it, you get exactly a cone. So if I want to find the area, the surface area of a cone is actually nothing more than the area of this piece. So that's the surface area of a cone. So the surface area of a cone, I open it, I get this picture, is the area of this piece right there. How much do you think I have from here to here? Suppose this is R. How much do you think I have here when I open it? Which piece do you think it opens like that?
Your circumference?
It's the circumference that open like this. This is the one which will open. So if you cut this and open it, this piece is going to be like that. So this is going to be basically the 2 pi r. And this one here, where you cut it, this will be from here to here. So boiling to what's really boiled down to is that opening this cone will give me this sector. So finding its surface area is actually finding the surface area of that. All right. Now a little bit of math, a little bit of trigonometry would tell you the following. This is just, you can memorize this. There is the following. If this is the angle theta here, then the theta is the ratio between the length of the arc and the radius of that. So there is an old formula that tells you that's what the angle is. So the area of surface area of the cone is the area of the sector. Area of a sector. Now what's the area of the sector? I don't know if any of you remember the formula from high school, I guess. It's a half times the radius of the sector here times the angle at the center, which is a half L squared over L. So I know that you guys forgot all those formulas, which is okay. So this is going to give me pi times the radius times L. So if you have a cone, the surface area of the cone is, this is the lateral surface right here. So it's the radius times the length times pi. Okay. All right. So these are basic shapes. And now our question is the following type of surface. Our problem is the following. As I said, in this problem, in this section, I will give you only the formula. So this is our problem. Let us consider the following problem. Okay. We're going to take the graph of a curve and I'm going to take a curve. That's my curve. That's my point A. And that's my point B. I'm going to take those kind of solid. The solid obtained as follows. We take a curve. And we rotate the curve, not the region, just the curve, because we want a surface. We rotate the curve around the x-axis. So we're going to rotate the curve. Okay. Not the region. We just rotate the outer curve. When we rotate this curve, it's going to generate a surface. And the question is, what's the surface area? So it's like if you take a simple line segment you have here. And if you rotate the line segment by itself, not the region inside, just the line segment, this is going to generate a cone. And I'm interested in the surface area of the cone. So we're going to do that cone again, one more time. Here I gave you the geometry of the problem, and then I'm going to do it again, not with geometry, without geometry, it's in calculus. So that's really what I'm interested in, is the surface area obtained by rotating a curve around the x-axis. So this time it's not the whole region, so this is hollow, this is totally hollow. I'm only interested in the outer layer. So here we're going to consider the following problem. Okay, find the surface area. So surface area of the solid obtained by rotating the graph, only the graph of the function y equal f of x for x between a and b about the x-axis. Okay, so the surface area, it means the area of the lateral layer obtained by rotating the graph of a function for x between a and b about the x-axis. And as I said, this time I will give you a little bit the formula and kind of give you a hint where's the formula coming from without going through the whole detail. It's given by the following integral. Integral from a to b of. Sometimes we write SA for surface area. 2 pi times f of x times the square root dx. Okay. And so the formula is 2 pi times the value of the function times the square root. This should remind you what we did in the previous section, dx. I'm going to do problems, but I'm going to tell you intuitively, and this time only intuitively, where is this formula coming from? Let me
I
explain.
have a question.
Yes.
So this equation will work for any surface area then?
A revolution obtained by rotating.
Okay.
It has to, yeah, it's very clear. It's obtained by rotating.
All right.
Okay. So if you give you any area, any surface area, and you realize that you can get the surface area by rotation, then you apply the formula.
Okay.
Right? Okay. So intuitively, how is the formula coming from? And honestly, all the formulas here are coming by cutting into pieces. So the idea of, again, is the same thing. We're going to cut this into pieces. Okay, so just I'm giving you a very, very kind of intuition where the formula is coming from, not accurate. So we cut into pieces and we rotate every piece. So if I take a typical piece and I rotate it, that's intuitively where it's coming from. Okay, we're gonna get something, not quite a cylinder because this piece here is tilted, but we're gonna get a piece like that. That's the piece we're gonna obtain. Now, what's the surface area of this little piece? If I call this xi, the surface area is gonna be almost equal to, if I open this, almost equal to the circumference from here to here times the length of that. That's what the surface area is going to be. So it's the circumference times the length of this little piece. What's the circumference from here to here? I call this xi. The circumference is 2 pi times f of xi. That's the circumference. The length from here to here, and that's where I'm waving my hand a little bit because I'm kind of thinking, you can think of this as a height. This is almost equal to the square root of 1 plus x prime I squared times the delta x, because that's the arc length that we got it from before. And that's really what the formula is coming from. 2 pi f of x represent the circumference of this little piece. This term here represents this little length. So when we multiply the circumference by the little bit of a height, I get the surface area of one little piece. And then I'm going to add the surface area. That's really how the formula is justified. Okay, now we're going to use it to find the following. So we're going to use it. Hopefully, I can do 2 simple problems with that. So example number 1. So a very simple example. Find the area of the surface. Find the surface area of the solid obtained by revolving y equal x, or f of x equal x, or y equal to x, for x between 0 and 1 about the x-axis. Okay, so find the surface area of the solid obtained by revolving f of x equal x for x between 0 and 1 about the x-axis. So let us see what the picture is. Of x equal to x equal to 1. And this is where I'm gonna get a cone. But now I'm interested in the surface area of this cone. All right. So we're gonna use the formula verbatim, which is simple, of course, in this scenario. What's the surface area? Remember now it's not the length, the surface area. The integral from 0 to 1 of 2 pi times the value of the function times the square root dx f prime x. So first we are interested in the derivative. F of x is x. It means f prime is equal to 1. So the surface area becomes integral from 0 to 1 of 2 pi. F of x is x, the square root of 1 plus 1 dx. So it's integral from 0 to 1 of 2 pi x. This is the square root of 2 dx. And finally, this would give me 2 pi square root of 2 integral from 0 to 1 of x dx. Now evaluate this. This will give me a half x squared from 0 to 1. And this will give me 2 pi square root of 2 times a half minus 0, which will give me pi times the square root of 2. And that would give me the surface area of this cone. Right. Let's see if our formula agree with the geometric formula I gave you at the beginning. And I will remind you, of course, what it is. Okay. At the beginning, I told you that if you have a cone and L is this lateral length from here to here, then the surface area is pi times the radius of the cone times the length of this side. That's the geometric formula. Let's see if it agrees, I mean, of course it will, with our problem right here. So pi, so it should be pi times r times L. So let's see if this is pi square root of 2. Okay. What is the radius of my cone in this particular problem?
1.
That's 1 from here to here. That's 1. What is L in this problem? Let me explain what L is. L is from here to here. That's the L. What's the L?
You'd have
What?
to do Pythagorean theorem.
You have to use Pythagorean theorem. Exactly. This is 1, and this is 1, 1. Okay, so how the geometry is agreeing with the calculus. So Pythagorean theorem tells me L squared is 1 plus 1. It means L, which is 2, L is the square root of 2. So this is, I'm doing it geometrically now, that's the square root of 2, and this will become that. So definitely the geometry, so that's geometrically, but it's just a cone, you know, that's the simplest possible shape. That's geometrically is pi square root of 2, and using our formula, we're exactly getting pi times the square root of 2. Okay. Now the other problem that I can't do because I lost sometimes was, and I want to do, perhaps it will be a homework for you. Let us say I have I rotate a circle, half a circle. So that's a circle. Let us say the radius is, I don't know, 5, for example. Okay. And I rotate the circle around the axis. What should I get?
Here.
We get a sphere. And the question is, what's the surface area of a sphere? And we can use exactly this to find the surface area of a sphere. Now, what's the equation of a circle? Does anybody remember the equation of a circle? So to be able to use the formula, we need actually to know the equation. It means we need a formula. If I know x, what's f of x? Anybody knows that before we go?
Pi r squared.
No. What's the equation of a circle? Anybody?
X squared plus y squared.
X squared
Equals r squared.
plus y squared equal r squared. That's the equation of a circle. Why? Pythagorean to the rescue. All the time is the Pythagorean. Because if I take any point on the circle, if this is the x and this is the y, Pythagorean tell me x squared plus y squared should be equal to 5 squared. That's really Pythagorean theorem. That's where this whole equation is coming from. So this means that the y of a circle, and this is something I basically expect my student to know, but after I explained it, of course, it means the y is the square root of 25 minus x squared. Okay. So now the question is, if I want to find the surface area, I have to apply verbatim the formula for this function, and I can find the surface area. All right. And I will do that tomorrow, definitely, because we have to connect what we're studying with something, of course, and tomorrow we're going to do that. Actually, we're going to find the surface area of a sphere. So if you take a sphere, what's the surface area? It means basically, imagine you take the sphere and then you take a scissor and you cut it and you lay it down. That's exactly what we are be looking. All right. Any question before I let you go? Sorry for the inconvenience at the beginning. I have no explanation to it at all. All right. Any questions? All right. Did you please start the review? Please start the review and go over the quiz for those who didn't do well. Make sure you get your mistake and come and ask me questions. All right. Anything? All right. Your homework will be on MATLAB in probably 4 minutes, and then you can do it for tomorrow. Goodbye, guys.
Thank you.
Go on.